Another great paper in the space of large language model training named Physics of Language Models. The paper delves into scaling laws for large language models, LLMs, highlighting a unique perspective by quantifying the knowledge capacity in bits rather than using conventional benchmarks or loss metrics. It pinpoints a remarkable finding. LLMs can store a maximum of 2 bits of knowledge per parameter. Consequently, a 7B model can store 14B bits of knowledge, surpassing the English Wikipedia and textbooks combined. All LLMs can achieve such 2-bit/param if sufficiently trained, even if all the MLP layers are removed. This is quite a universal law. When we say the model stores knowledge, it isn't word-by-word memorization. Instead, the knowledge is flexibly extractable. How training time affects model capacity, as per the paper. Achieving a 2-bit/param capacity requires each knowledge piece to be visited 1,000 times during training, termed 1,000 exposure, to differentiate from traditional 1,000 pass terminology, as a single data pass can expose a knowledge piece 1,000 times. Knowledge representation. The research categorizes factual knowledge into tuples, name, attribute, value, providing a structured and quantifiable approach to understand and measure knowledge within LLMs. The researchers generate synthetic knowledge-only datasets by uniformly at random generating name, attribute, value, tuples from a knowledge base and converting them into English descriptions. They pre-train language models, for example, GPT-2, Llama, Mistral, on these texts using a standard autoregressive objective from random initialization, and estimate the learned knowledge. By varying the number of knowledge pieces and model sizes, we outline a knowledge capacity scaling law. Influence of various factors on knowledge capacity. Architectural features, like GPT-2 with rotary embeddings, and quantization, even down to int8, do not compromise knowledge storage efficiency. Training data annotation with domain names enhances the model's ability to prioritize and absorb relevant information. Models display stable knowledge capacity regardless of the diversity in hyperparameters such as model size or data size. Practical implications for model training and deployment. The paper's insights can streamline the design of LLMs, suggesting that beyond a certain threshold, adding parameters does not linearly increase a model's knowledge base. It underscores the significance of thoughtful data preparation and architectural choices, emphasizing that models can achieve high knowledge efficiency with proper training regimes and data annotation strategies. Empirical verification. Through extensive experiments across various settings, the study provides robust evidence supporting its claims about knowledge capacity and the influence of model and data characteristics, ensuring these findings are grounded in empirical observation rather than theoretical speculation alone. Broader applications and future directions. The insights from this research could influence future developments in LLM design and training, proposing a shift towards more knowledge-efficient models that leverage advanced embedding techniques and data pre-processing to maximize their information storage potential. The point regarding the influence of architectural features and quantization on knowledge storage efficiency within large language models, LLMs, as explained in this paper, underscores the resilience of these models in maintaining their knowledge capacity despite significant changes in their architecture and numerical precision. Architectural features. The incorporation of rotary embeddings in the GPT-2 architecture is highlighted as a beneficial modification. Rotary embeddings enhance the model's ability to capture positional information more effectively compared to traditional positional embeddings. This feature is crucial for understanding and generating language sequences, and its effectiveness in this context suggests that it does not hinder the model's knowledge storage capacity. Despite these architectural modifications, such as the transition from standard positional embeddings to rotary embeddings in GPT-2, the model maintains its ability to store up to 2 bits of knowledge per parameter. This indicates that the enhanced encoding of positional information via rotary embeddings does not compromise the overall knowledge capacity. Quantization. Quantization reduces the precision of the model's parameters, typically to lower bit representations like int8, which drastically decreases the model size and speeds up computation, especially in deployment scenarios. The findings suggest that quantization to int8 does not degrade the model's capacity to store knowledge. Even when parameters are quantized to int8, which inherently reduces the granularity of the information that these parameters can represent, the model retains its knowledge storage efficiency. This resilience implies that the essential knowledge representation within the model is preserved effectively, even in a reduced precision format. The study's conclusion that quantization down to int8 does not impair knowledge storage efficiency is significant for deploying LLMs in resource-constrained environments, ensuring that the models remain effective while being more computationally efficient. In summary, the paper illustrates that architectural advancements in embeddings and the application of aggressive quantization techniques do not detrimentally impact the knowledge capacity of LLMs. These findings are crucial for the design and deployment of efficient and effective LLMs, enabling the development of models that are not only powerful in terms of their linguistic capabilities but also optimized for computational resources.